Okay, good afternoon. I'm Chris Greer. I'm Director of the Smart Grid program here at NIST. Thank you for joining us for this webinar today. To get started, let me provide you with just a little bit of background to get us going. NIST, the National Institute of Standards and Technology, is a bureau in the Department of Commerce, and we serve as the research arm of the department. Through the Energy Independence and Security Act, Congress assigned to NIST the responsibility to coordinate the development of a framework for smart grid interoperability. And my office is responsible for fulfilling that requirement. In their mandate, Congress used the word coordinate quite deliberately, intending that NIST would work with a full spectrum of stakeholders in developing a consensus framework. In keeping with that expectation and with long-held NIST practice, this event represents the launch of the consensus building phase of our work to develop version 4.0 of NIST framework and roadmap for smart grid interoperability. That goal, building on consensus, is why we're very glad that you've joined us today and why we hope that you and others throughout the sector will join in the upcoming events that you're going to hear more about here during the webinar. These events will also be an opportunity to find out what your colleagues and counterparts are thinking about the future of the grid. So please stay engaged throughout this process. So again, welcome to the webinar on behalf of NIST, and let me turn it over now to Avi Gopstein, who's the director of our Smart Grid program, who will lead us through the rest of the webinar. Avi.
All right, thank you, Chris. We have a lot to cover today. So we will be brief in how we cover some of the slides. There will be a number of workshops and feedback opportunities that Chris mentioned over the coming months where these issues will be explored more deeply, and we encourage you to be involved in that process. For today's webinar, we'll begin with some background on previous versions of the NIST interoperability framework and take you through some updates that we are proposing for the NIST Smart Grid conceptual model, as well as the development of communications pathway scenarios. And from there, we'll go on to discuss a new language, CPS ontology, that we can apply to the smart grid, and then dive into a few key framework messages on operations economics, cybersecurity, and testing and certification. And at the end, we'll provide web links and other information on a number of workshops that we already have in process and which we hope to see you at in person. So 3 frameworks have been published to date. The first framework took a snapshot at the state of smart grid interoperability standards and also identified gaps in standards that were later addressed by activities of NIST and other organizations. The second and third frameworks were incremental updates, which focused on progress towards addressing the standards gaps identified in the first version, and also updates to the smart grid conceptual model. So here you can see versions of the smart grid conceptual model that appeared in earlier versions of the framework. The important concepts that were introduced by these models include a distinction between the physical flows of electricity and the communications which allow the system to operate. So note that the physical flow of electricity is relatively limited. That is represented by the dotted dashed lines in black at the bottom in the first version on the left, and in gold in the third version on the right. But this is a relatively limited subset of interactions when it comes to the grid. Also, through the description of 7 smart grid domains, people and organizations could understand their role and interactions within the grid. You can also see a change from the 2010 to 2014 versions, the first and the third versions of the conceptual model, where the transition from linear power flows to more complex system dynamics is represented in the separation and increasing complexity of interactions between the generation domain and others. There are a number of motivations as to why we are embarking on the 4th version of the interoperability framework. First, the pace of technological change is accelerating, and the modularity of technology means functions once limited to specific domains or actors can now penetrate other parts of the system. Distribution and customer domain behavior used to be relatively simple. from a physical perspective, where typical consumption and voltage drop along distribution lines allowed head-end management of services and other such things. Now, the harmonics of digital loads, the possibility of two-way power flows, and other issues create uncertainty throughout the system. So as we look into these issues, we have identified a number of themes to be included in Framework version 4. First is that grid architectures affect the operations, economics, and cybersecurity of the system. The impacts on these aspects of the system must be well understood if we are to properly characterize the evolving interoperability needs. Also, actors are taking on new roles within the system. These roles can be intentional or unintentional. For example, somebody who puts a PV system on their roof may not intentionally be joining the generation domain, but in process they have. Also, there are new physical and economic forces emerging within the system as capabilities penetrate and diffuse through other domains. Because of this, interoperability gains new dimensions. There are the physical interactions of the grid change, the information exchange between devices increases, and the information exchange across domains increases similarly. So now we come to the update of the smart grid conceptual model. This is a draft. All the images that you will see in this presentation are draft updates to models and diagrams, which we will explore with you both today and through future interactions at the workshops. A couple of important changes to the smart grid conceptual model for this revision include distributed energy resources being incorporated into the generation domain. This reflects the technology diversity of what is considered generation as a system is operated and optimized. And also we have extended that domain on the bottom of this model to call attention to the physical proximity of generation and DER to the various other domains with which it interacts. And that includes the transmission, distribution, and customer domains. Another major update is the focus on an intelligent distribution system. Graphically, we've represented that in this model by increasing the importance of the distribution domain. The size of the domain is a bit larger than previous. It is also moved a bit more central with respect to the grid. And there are devices and equipment represented in that domain graphic that allude to the improved controllability and intelligence within the system. Another important change is the connection of the distribution domain to the service provider domain, which did not exist previously. Another major update is that of an empowered consumer. Operations and intelligence has entered the customer domain, and customer diversity is incorporated when you look at this graphic compared to previous versions of the conceptual model. Each of these domains has a rich set of information and data contained within it. There is a lot of information that goes into the graphical representations and our understanding of communications and physical power flows. Right here you can see the breakout of the generation domain, which is the generation including DER domain. The major change in this representation is that electrical flows now enter the distribution domain directly. This was not represented in previous versions of the conceptual model. And we also have an update to the communications within the system, where previously communications would focus on local control and protection and other applications. Moving forward, the inter-domain communications flows will have increasing importance. Moving to the transmission domain, the transmission system optimizes over a wide area, and while it may contain distributed energy resources, such as electrical storage or peaking generation plants, these are generally utilized to support the health of the broader system. Transmission level outages are exceedingly rare in this country, and the system is designed and operated at this level to manage any major contingency to at least the N-1 level. The distribution domain is seeing some of the most dramatic changes in the grid today. There are new sensors, and those are indicated here as opposed to the previous conceptual model versions. And the distribution domain communications are more granular in fashion with the other domains on a wider array of issues. There are new responsibilities assigned to the distribution domain, including stabilizing the system, which is now part of distribution system priorities and operations, as contrasted to previous conceptual diagrams. As we go to the customer domain, it's interesting that this graphic is relatively unchanged from previous conceptual model iterations. But what's interesting is that as the previous vision is realized, the customer domain becomes a larger focus as we explore specific communications and interoperability interfaces. In the markets domain, communication flows between the markets domain and the domain supplying energy and services are critical because efficient matching of production with consumption is, in some form or another, dependent on markets or proxies thereof. In the abstract, the markets domain is also largely unchanged from previous versions, as it represents an economic approach to optimizing the system and the communications that are required. The role of the operations domain is increasing in complexity, and the communications requirements are growing substantially. We anticipate through our stakeholder engagement that this domain in particular will evolve further, especially as we engage in regional workshops through the latter portion of the summer and early fall. Here, the service provider domain has been expanded. Where in previous versions service providers were limited to providing services for other organizations, we have introduced the energy management role. And this is an acknowledgement that service providers can and are taking active roles in optimizing the grid through the management of their own assets, in addition to the work that they did and still do for others through building management, home management, and providing services to utilities. But as rich as the conceptual model is, the representation of communications pathways and interfaces are limited. To help explore these interactions, diagrams were created to illustrate communications networks in a smart grid scenario based on the conceptual model. Here you can see the diagram, which was created for the third version of the interoperability framework. This highlights some important communication interfaces between and within domains as applied to our smart grid concept at the time, and it was formulated in partnership with the stakeholder community. But grid architectures are not consistent as they were 4 years ago. Dramatic change and diversification is occurring in many domains, and single communication scenario can no longer capture the richness of potential grid operation approaches. So therefore, in Framework 4, we are using this communication diagram as one scenario, our legacy smart grid scenario, within a range of scenarios to be considered moving forward. I want to emphasize that these scenarios are not architectures. Instead, they are explorations of communications interfaces one could possibly see in a range of future grid systems. Here we have a high distributed energy resources communications pathway scenario. There are a number of changes that you'll notice from the previous diagram, including the generation, including DER, wraps around transmission and distribution domains and overlaps with the customer domain. The differences in these two approaches, touching a domain versus overlapping a domain, shows the different roles these assets take. In the typical generation and DER domain, which does not overlap another domain, the priority of the asset is to support the grid function. In the customer domain, grid function may have to compete with other priorities for the utilization of the assets. In this diagram, we have also simplified the communications interfaces wherever possible, often drawing lines into the domain or subdomain rather than to the individual actor. The purpose of this is merely for visual clarity to identify a higher level interface while preventing the complexity in these scenarios from overwhelming the eye. It is not meant to indicate that these interactions or interfaces somehow are no longer driven all the way to the actor as they were in the previous diagram. Finally, the existence of multiple control loops and the possibility of multiple interface requirements for the same asset is shown through multiple connections. For example, the smart thermostat in the customer domain may connect directly to a building automation and control system, but also through the internet to a customer app or through the utility meter into a utility demand response regime. That same thermostat may now also interact with more than the HVAC, the air conditioner or heater, but also with other devices around the premises. This complexity is represented by the communications pathways control loops that you see here. Here we show our microgrid communications pathway scenario, which acknowledges the role of a master controller as providing structure to the operations and optimization strategy for new technology. In this scenario, the microgrid master controller also serves as the key interdomain interface, which has implications for the interoperability performance requirements of that actor. By having two different microgrid configurations, we can explore that generation and other assets exist in different management contexts. There may also be differences between customer and utility managed assets. And while high-level leads may be similar, for instance, local reliability, the implications for grid services can be explored by assessing these different structures. Our hybrid utility communications pathway scenario facilitates understanding of roles and communications in centralized, distributed, and edge systems. It explicitly acknowledges that the edge of a system is actually domain dependent. The edge of the transmission system is fundamentally different from the edge of the customer system. We'll explore this further in some future slides. So we've just gone through a dozen or so slides to talk about the smart grid conceptual model and these communication pathway scenario diagrams. These diagrams are complex. And in the smart grid space, jargon is ever present and sometimes hides what needs to be done. Using precise language brings clarity to the conversations that we have to have around not only these complex diagrams and concepts, but the actual implementation in the field. The Cyber Physical Systems Framework, which was published, I think, last year, provides a vocabulary through which we can be more precise about the smart grid and gain clarity over specific parts of and requirements for the smart grid. To explore this further, let's examine the list of cyber physical systems aspects and their associated concerns. In the previous slide, there was a graphic that showed aspects on the left and concerns moving along the top, and what you have is an ontology that helps describe different functions and characteristics of a system. What I've done here is I have detailed the 9 aspects included within the framework of a cyber physical system, and also the 39 concerns distributed across these assets. But when we think about something like grid intelligence moving to the grid edge, it actually touches many concerns across the cyber physical systems framework and the system itself. High-level language like intelligence obscures the specific concerns that must be addressed to provide a new capability to the system. For example, intelligence requires an awareness of system behavior. Awareness for intelligence requires sensing, of course, but also some specific measurability of the parameter which will be optimized through the application of intelligence. But measurement alone doesn't mean you can do anything with that data. So you must also be able to monitor the system at the correct location to implement intelligence, which means you have to communicate the data in a time-aware manner and have the data semantics worked out so that the output of your sensor is properly interpreted by the intelligence agent. The importance of this cannot be overstated because what we're trying to do is clarify the specificity of action and relationship across an incredibly complex system like the grid. So for Framework 4.0, we have drafted grid context and description statements for each of the CPS aspects. It is our position that having this language, this ontology, will enable improved communication and specification of performance, of function, of capability, and of the interaction and interface between different actors and assets. We plan to obtain feedback on these descriptions at our July 24th and 25th workshop, which I'll describe later in the presentation, and we invite your participation. So here we have some themes for the framework which we are exploring through the pathway scenarios. The scenarios that we've described in the previous diagrams, they affect what we think about the grid. Those communications, interfaces, and pathways affect our understanding of cybersecurity, of operations, and of the economics of the system. We can use these examples to explore common trends, changing responsibilities, and the unique considerations of one structure versus another. Scenarios also help us understand value streams. For example, who is the customer in a high DER structure? When the customer domain has assets that provide voltage support to the distribution domain, the definition of customer has to change, and these scenarios help us explore that. These scenarios are also critical to helping us understand the role interoperability has in unlocking these value propositions. Testing and certification in this new environment grows in importance. We have many examples when claimed conformance to a standard versus actual device performance are not the same. As intelligence moves to the edge of the system and controllability does, actuation and controllability will be in every device. And as the owner and responsible party for a device changes, as these capabilities penetrate into other domains, we need a way to understand, to enable unified operation to achieve our goal, which requires interoperability. The CPS ontology allows this level of description and specification. Right here on the right, I also want to highlight the engagement opportunities. We've mentioned them a few times before. On July 9th, we will host a testing and certification workshop in Washington, D.C. as part of the Smart Electric Power Alliance Grid Modernization Summit. On July 24th, we will hold a communications pathways and ontology workshop in Gaithersburg at NIST. And through late summer and early fall, we will host regional workshops in partnership with the National Association of Regulatory Utility Commissioners and state-level commissions to explore operations and economic workshops. We'll have more details on these events in the slides at the end of the presentation, Registration is open for some of these events. We have web links, and we encourage you to participate. So we've gone through the history of the interoperability framework and the context, as well as the updated models that we're using to explore these key themes of changing operations, economics, cybersecurity, and testing and certification. On the next set of slides, we'll explore key messages relating to each of these aspects of the system. So one key message regarding operations is that sensing, intelligence, and control continues to push toward the grid edge for each domain. And centrally dispatched managed generation and other resources can span all geographic areas of the grid. So right here, the Operation Enterprise Service Bus, as part of the Operations Control Center, communicates towards the edge of the system. And that edge of the system includes communications that go to the edge of the distribution grid, to the edge of the transmission grid, and to the transmission system, and also towards the customer. Another key issue for system operations in a highly distributed environment is one of shared infrastructure. Not only do the number of interactions increase, both locally and with central operators, but exclusive use of dedicated communications and control infrastructure may no longer be feasible. Questions we hope to address at our workshops include: what is the important interaction class to focus on for interoperability in the high distributed energy resources scenario? Is it the inter-domain communications? Is it the intra-domain communications? Or is it when the communication changes from one organization to another? We also intend to explore what can be done to mitigate the risks of shared infrastructure as we consider cybersecurity implications, performance limitations, and others. Another key message about the operation of the system moving forward is that no single architecture is the correct architecture. Again, I'd like to emphasize that NIST scenarios are explicitly not architectures, but they are ways in which we explore architectures being used and developed by others. But to this end, and the fact that there is no single solution, let's explore a single utility in Minnesota which has employed some demand response programs. The demand response program, one of which uses voluntary curtailment of large industrial loads, and this is shown on the green page on the left of the slide. Another one of this utility's demand response program utilizes direct load control of heating and cooling assets in customer homes, and this is shown in the blue paper on the right. What's important here is that the voluntary curtailment approach, that green scenario on the left, is very similar to a customer-owned microgrid scenario. You can see that we've circled from that earlier diagram the microgrid master controller and the customer-owned microgrid scenario. In this implementation, the Minnesota utility, Dakota Electric, calls or emails the campus operator and indicates the need for curtailment. The campus operator makes their own decisions on how to achieve the needed change, and they are responsible for executing that. Essentially, the campus operator is the microgrid controller in this scenario. On the other hand, the direct load control program in the blue on the right is more akin to our high distributed energy resources scenario, where the utility has direct control over the heating and cooling assets in a customer's home, either in the winter or summertime, to manage the load on their system. Another operations key message is that of diversified ownership across the system. So we've discussed previously how capabilities are penetrating new domains, and with that, the view of what a typical asset is that would help or contribute to the overall operation and well-being of the system is changing. This diversification comes with a host of other questions. First, diversifying of purpose. So for example, is an electric vehicle there for transportation, or is it there for grid services? Probably transportation is the first optimization function, grid services is the second, but that creates some uncertainty in how the system is operated and what needs to be communicated about it. We also have diversifying concerns over maintenance. How well do you know the current physical parameters of an asset if that asset is in another domain owned by somebody else? Finally, we have diversifying availability of assets. If there are multiple optimization functions, it's not clear that an asset will always be there for your intended purpose, regardless of what your purpose may be. Interoperability in this context has to be improved. There are dozens of communications protocols, dozens of data models and their derivatives, and given the questions above, we need to understand how much more an operator needs to know about an asset to gain confidence in its performance. In this context, trustworthiness extends into operation. So can homes with microgrid controllers be treated the same as commercial and industrial microgrids? Can homes with electric vehicle chargers be treated the same as an electric vehicle charger in some sense is the equivalent of a microgrid controller? Can homes with a thermostat platform be treated the same as a microgrid? And what about specific devices? Testing and certification is critical to the demands for increased interoperability and trustworthiness in this system. On to some of the economics key messages. Interoperability can help overcome the barriers of device specificity and support the marketing efforts and revenue outlook for new and existing grid services. In general, things are purchased for a specific function. Capabilities beyond that specific function or competency are generally not free of cost and require an increased investment. For long-lived components of the grid, new functions for existing assets can evolve over the asset lifetime, and interoperability provides a means to expand functionality beyond the original design. We have an example of this ongoing in California right now, where behind-the-meter storage was originally deployed for managing customer demand charges. Now, as storage becomes a more integral resource for distribution and bulk operations through aggregation and dispatch, the original functionality of the deployed storage is expanding as the interoperability allows communications across new interfaces. Another key economic message is that interoperability is crucial to customer empowerment. First, through enabling customers to be better informed regarding their own electricity use decisions, but second, through enabling a plug-and-play environment in which these better-informed customers may bring a device of their own choice for integration with the rest of the grid. The modularity of technology is delivering ever more capability into new grid domains and into the hands of customers. For customers in particular, increasing information and control over technology and resources they own, as well as their interactions with the grid, enable new opportunities for investment and the realization of returns. Interoperability also has the potential to mitigate rising transaction and production costs associated with the increasingly complex interaction of organizations that constitute the electric grid value network, including customers. This proposition is especially important as regulatory structures affecting participation and remuneration can change as function of geography and system topology for a given asset. Transaction costs have long been noted as a barrier to market formulation in the classical economic sense, and interoperability can mitigate cost escalation due to the growing complexity of the system. The development of effective and affordable testing and certification regimes can provide the level of trust or assurance needed to accelerate adoption rates for emerging technologies and engender the growth of new revenue streams and business models in the electric power sector. As we transition into our cybersecurity discussion, I would first like to highlight that NIST is in the process of creating a cybersecurity risk profile for the smart grid. Based on the NIST cybersecurity framework, this risk profile provides a structured approach to the necessary evaluation of cybersecurity considerations for power systems and how these concerns adjust as a function of system architecture. Some interesting conclusions that we have are that we anticipate that the business and mission requirements of the grid do not change regardless of system structure. But as new asset ownership models develop, the responsibilities for these objectives and mitigating cybersecurity risks changes hands. There are therefore various considerations about how to achieve desired outcomes. These considerations will be highlighted for various communications pathway scenarios in this framework and future NIST publications. If you'd like to learn more about the NIST cybersecurity framework, there is a link on the page which you can go to. As distributed energy resources and edge intelligence is incorporated into the grid, communications and associated cybersecurity risks also increase. On the left, you can see a diagram from a 2010 NIST publication on smart grid cybersecurity. And on the right, you can see our explosion and update of some of those communication pathways for our high distributed energy resource scenario. The risk associated with each individual communication can likely be categorized or grouped against conventional cybersecurity wisdom or logical interface categories. So you can see on the right, we have blue arrows, which are drawn explicitly and directly. Those represent interfaces and communications drawn explicitly and directly from the diagram on the left, which was published 8 years ago in that NIST report. In the diagram on the right, you'll also see red arrows. Those arrows represent new interfaces that we are calling out as we explore the high DER communications pathway scenario. What's important here is that as we evaluate these interfaces and these new communications, we are still able to map these new communications to the existing IT community logical interfaces and conventional wisdom. So these, even though communications are expanding, it is a known problem in the IT space that has already been evaluated, even sometimes for the grid, although it may be new to this specific application or domain. So this combination of known issues and new interfaces then map into the cybersecurity risk profile for concerns, and strategies for mitigating cybersecurity risk can be developed based on known best practices. The important takeaway here is that even though we have new concerns, the sheer volume of communications channels, the distributed nature of the communications, the questions about ownership of device and whether or not they can be trusted, and these lead to questions of control and data integrity, the interfaces, the issues are known and can be incorporated from the knowledge and best practices of other areas. Now we'll move on to some testing and certification issues, which Kun Nguyen will describe.
Thank you, Avi. So I think as you heard, Avi, testing and certification has grown important as we consider work for version 4.0 of the framework. So in order for us to actually take a look at the current state of testing and certification for smart grid standard, we wanted to pull together a list of standards that we can actually evaluate for availability of testing and certification related to those standards. So we identified three main sources of standard. The first one is the Smart Electric Power Alliance SEPA catalog of standard. And the second list is the Smart Grid Standard list that came from our version 3 of the NIST Smart Grid Framework. And then the third source is the Distribution System Operator Priority List. However, because the fact that you have a catalog and a list, they become static. So we have to actually look at all these standards and identify any new version of standard that are available. So that's the fourth source that we actually consider for evaluation. And through all of these sources, we actually took a look at 244 individual standards that span across over 30 family of standards. So it's a quite big list. However, I want to make sure that this is not an exhaustive search, right? We want to have a set of standards that we can evaluate. So this is not all-encompassing standard list by any means for smart grid, but it's just a way for us to actually conduct our analysis. So in order for us to do a comprehensive analysis, we want to group these standards based on a different approach, right? Because normally you could see standard being grouped in domain or subdomain or component or function, but we had trying to come up with a more granular way of actually grouping them, and we came up with these following categories. So we grouped them based on information model, communication, physical performance standard, test methodology, communication mapping, so mapping between communication protocol to make them interoperable, information model mapping as well, to address interoperability, guideline and best practices, and then security is the last piece. So based on these categories, we kind of bin the 244 standard into these categories so that we can actually look at testing certification availability for these standards. So in our preliminary analysis, we focus on three categories of standard, the information model, communication, and performance. And the reason for that is, we believe that these are important, standards to be addressed. And the other part of this motivation is, there's the guideline and the communication and information model mapping are not those that you can actually build a test program around. So we kind of haven't actually addressed those as far as how we want to capture testing certification approaches to them, because they could be part of the main standard or the map standard, right? So I think those we haven't actually gone to. So we picked these three high-level categories to have a more seamless or at least easier analysis. So of those standards that we looked at for the information model, 16 out of 61 actually have a TNC associated with them. And for the communication, 25 of the 114 actually have TNC. And then for the physical performance standard, 14 out of 30 actually have them. So if you look at the percentages, for information model, it's about 26% that have TNC. For communication, it's 21. And then for physical performance, it's about 47. So as you can see, there's definitely a deficiency in availability for information model and communication standard, for TNC. Performance is actually quite good, but still not 100%. So with that in mind, some of the key messages that we want to explore in the testing and certification is that the gap does persist in ensuring interoperability because, as you can see, there is a big growing list of standards that is the foundation for grid modernization. So standards are evolving and growing, but there is still a gap of availability for test program to the standard, and then the importance of that is the test program ensure that the standards are implemented correctly and consistently, so then you can support interoperability of devices and systems. However, I just wanted to point out that even if a standard is conform or to the if a device or a system is conformed to the standard, you still have to integrate it, right? So it doesn't mean that automatic interoperability. I mean, we do want to go to plug and play, but that's still something that you have to consider. So with a testing and certification regime, you can have more assurance that it would work, but there's still that integration part that you have to take up. And then the other two item is that we saw that the industry is coalescing around a subset of standard and option, but there's still a really big universe of standard and for an application that are kind of diversifying as well. So they're not totally unified around a subset. And then the other piece is that some standards are showing conversion, but the requirements sometimes are on parallel pathway. So this creates more complexity in the development of testing and certification that I would touch on next. So here's an example of an implementation complexity. So we pick a recently approved standard, the IEEE P1547. It is a standard for interconnection and interoperability of distributed energy resources with the power system interfaces. So this is a critical standard, as you can see that, now with the whole penetration of DER and availability. So, it is an important standard. However, if you can look at the allowable communication protocol, the standard allows for 3 separate communication protocol. And if you implement one of these protocols, you can actually include other protocol as well, right? So there's multiple communications protocol that you can implement in the device. And then for the information model, the standard did not specify an information model. So, this actually could be a lot more. So in this example, we use just 3, a pair of 3 and 3 just for illustration purposes, but you could potentially have other. So with just the set, you can have up to 12 implementation of the standard. So actually that, increased a lot of complexity for the implementer as they actually build the devices, and for the integrator too, right? Because, you have to pick your protocol or data model that you need to integrate to. So because of that, we want to propose a tool of an interoperability profile, and a profiling approach is nothing new, but I think we want to focus on interoperability profile as a way of including necessary elements that can actually provide a subset of standard that the user community in the ecosystem can actually agree to. And we believe that a sufficient profile would include the physical performance of the device or system, a communication protocol, and a data model. And I think with those 3 elements, you can actually have a uniform implementation. And the benefit of making a profile is that it actually allows you to narrow the interoperability gap, right, by reducing the degree of freedom in the implementation. So I think this would be of interest to both the supplier, implementer, and the system owner, right, the deployer. So, we want to kind of propose this approach to actually help as a means to form testing and certification program around them. And then the profile can provide benefit, right, like I mentioned before, narrowing the constraint and provide uniformity to support multi-vendor interoperability and then to lower cost of integration. So with that background, we want to explore this concept further in the testing and certification workshop that's coming right up on July 9th in Washington at the Washington Hilton. It is being co-sponsored by SEPA, and the objective there is to explore. I think we kind of established the landscape of available testing certification that we need to push for more programs. So we want to explore the underlying driver for the current state of smart grid interoperability testing, and then also explore the interoperability profile for smart grid standard as a way to actually accelerate these program formation and to improve their availability. So with that objective, the key question we want to look at is, what is limiting the development of and use of T&C in the smart grid ecosystem? The next question is, what essential elements are needed to formulate an interoperability testing and certification program? And then the last one is how you prioritize operational interfaces in the testing certification development. And this kind of goes back to the interoperability profile, right? If you identify, prioritize the interfaces, then you can actually have a pathway to develop, a profile that will be needed to actually address those interfaces. So with those key questions, we have a workshop structure. We will make the agenda available shortly, with just putting some final touches on it. But the structure for the workshop will be to start with an open plenary, followed by a keynote address from a utility, and then we will have a panel session to look at the value proposition for the testing and certification program. And this is important because it is a business decision where you actually would want your product certified or not, because there's added cost, right? So we have to look at the value proposition because it is an added cost. But we want to make the case that there are savings if you actually get a certified devices or system. And then the breakout session would kind of address the two questions, the essential element of the interoperability program, and then the priority interfaces for TNC. And then after that, we'll do a report out and next step. And then on this page is a workshop link to the workshop page. So I encourage you to visit and register and join us. And one thing I want to note is this workshop is free of charge for the registration. There's no fee to attend. So we definitely encourage you to participate. And now I'm going to turn it back over to Avi to talk about this pathway scenario workshop.
All right, thank you, Jim. In addition to the testing and certification workshop, we also have a number of other activities we're planning both in the Washington, D.C. area and beyond. The first is our communication pathway scenario workshop. The diagrams that we showed earlier in this presentation are the foundation of our analysis into the operations, economics, cybersecurity, and testing and certification needs for the future of the grid. We want to be sure that the scenarios we are exploring are representative of what's actually happening in the system today and in the future. So we will host a workshop on July 24th and 25th at NIST in Gaithersburg, where we will ask participants to help us identify errors and deficiencies in the NIST communication scenarios. Maybe there are none, probably not. We also will explore ways in which we can utilize the smart grid conceptual model to convey these different grid scenarios. We hope there's a better way to communicate the richness of these diagrams without going into the detailed complexity that you see in some of them, and we'll ask for your help in doing that. We also will explore with participants improvements that might be necessary to the cyber-physical systems concerns ontology for the grid to make sure that we are truly capturing the concerns as relevant to the grid, and that we're not missing something or creating a vocabulary that that lacks some sort all the benefits it can bring to the discussion of the smart grid. The link on the bottom it goes to that web page. I do not believe the registration link is live yet, but it will be soon. We at the end of the discussion will give you a link to our general framework webpage, and you'll be able to get to all these other links from there as well. So keep coming back, and we'll keep you posted. You can sign up for our listserv as well if you'd like to be posted more regularly. We are also going to engage in some regional workshops. As I mentioned earlier, the operational and economic concerns can be regionally specific. They can be very local. They can also be consistent with everything else happening across the grid, across the country. So we have partnered with the National Association of Regulatory Utility Commissioners, NARUC, to explore regionally specific issues affecting grid operations and economics. We are going to hold workshops at 4 state public utility commissions, and this will allow both participants and NIST to learn about interoperability issues and concerns relevant to the respective commissions and their stakeholders. These workshops will be held in the Northeast, Midwest, West Coast, and Southeast, sorry, not Southwest. I have to update that, apologies. And we are in the process of identifying the specific commissions and the dates, and we will keep everybody informed and let you know as soon as those workshops are confirmed in both date and location. You can go to the link on the bottom or the link on the next page, which is our overall framework website. Again, participation in any workshop is free of charge, and so we hope that by hosting events around the country, as well as in conjunction with major conferences like the Grid Modernization Summit and on the NIST campus, that we can find a way for everybody to participate in at least one, if not more. This link right here is the website for the framework, and I encourage you to check back regularly. We will update it with content, with information about workshops. We will post the slides from this presentation on this website later today, and we will also provide draft and early material for discussion and comment and feedback throughout the course of this process. That's all we had intended to go through today. I do believe we have an opportunity for questions through the chat window. Let's see, we can just go through the questions. Francis, I understand your concern, and when you look at the domain breakout, I do believe all of these are incorporated in there. If they're not, we'll make sure that they are. Sorry, the question is, the statement is DER should include generation, storage, and controllable load, which is more than generation. We agree. We also need to keep the domain names manageable, and I think generation including DER is about as broad as we can go, but we'll make sure that the domain diagram does include that representation. Michael Sands asks if estimates have been made in terms of bandwidth needed and communication to be used for automated transactional purposes and how much for command and control purposes. We have not estimated the bandwidth yet. We have estimated the latencies necessary for certain control signals. We have the NIST program has a number of publications on those issues, and as we come out with draft chapters, you will certainly be able to read our perspective on the time constants for these communications and command signals as a function of different control signals. Michael Sams also asks what standards are being considered to promote scalability while maintaining security and reducing comms latency. We're not prepared here to discuss the totality of standards that relate to each aspect of the grid, but we certainly can and will provide the listings of standards that we use to evaluate the testing and certification landscape, as well as other sets of standards that we have relied upon. That will all be public prior to the July 9th workshop. And I think similarly for Francis Cleveland's question, which is about whether how much will NIST work with the IEC communication standards, namely 61850 and cybersecurity standards. Those are part of our evaluation processes, and those are part of the range of standards that we are considering. The IEC was a source of one of our sources for evaluating the constellation of testing and certification programs and smart grid standards. Vijay Ahuja asks which session will focus on cybersecurity accreditation aspects. That's a very important question. We are working to define when our cybersecurity workshop will occur. We want to be sure that we have a published risk profile before we schedule that workshop, so that all participants can come and understand the totality of, or not the totality, but the depth of work that has gone into this effort. And so after publication of the risk profile, which we will post on the framework website, we will schedule the cybersecurity workshop. Stephen Ray said, I don't see the ontology workshop listed on your website. Could you repeat that info? The ontology workshop is the July 24th and 25th workshop at NIST. That is the Communications Pathway Scenario Workshop. We're struggling to try and find a name that can accommodate all the things that we want to cover in that day and a half. But ontology will be included in that, and in the read-ahead materials, we will publish a draft of the ontology list for markup, feedback, and comment. Andrew Bowen asks, if we are an accreditation body, which workshop would you encourage us to attend? The July 9th workshop, I assume. I agree with that. The July 9th workshop is our primary activity focused on testing and certification of interoperability performance, and I believe your interpretation is correct. Bruce Nordman asked a few questions regarding the definition of distributed energy resources, as well as what hyperlocal refers to with respect to the utility distribution system. First, the definition of distributed energy resources does include flexible loads. It is anything that contributes to the energy balance of the system. Secondly, hyperlocal is meant to convey the fact that optimization strategies are now smaller and more constrained than not just feeders or circuits, but even subsets of feeders and circuits. So the optimization could be on an individual asset, or it could be on a home or a customer premises, or it could be on a neighboring aggregation of assets or customer premises. So that was not intended to be a quantitative statement. It was intended to provide a contextual language to describe the evolution of optimization and control strategies. Len House asks if the framework comprehends the trust supply chain lifecycle so devices with cyber risk can be identified and updated as needed. So that is a risk identified and described within the cybersecurity risk profile for the smart grid. How explicitly that is addressed is a question to be explored through the workshops and interactions. But essentially, asset maintenance and hygiene is a known risk and a critical component of cybersecurity risk for the smart grid, and it is included in the draft risk profile. Okay, we've answered the majority of questions posed to us. I think this concludes our webinar. I'd like to thank everybody for your participation and attendance, and I look forward to seeing each of you at one or more of our workshops. Thank you very much.